We're going to discover how work and energy relate on these videos. First of all, I have a pulley system with 4 support ropes. These red ones are just there for safety. And then I have a spring scale here to read the force. The first thing we need to do is we need to figure out how much mass that item has. Well, the object weighs, with some ropes on there, 1,020 grams. We're going to round that to 1,000 just to make our analysis a lot easier. Let's see how many newtons we have here. Notice that's zeroed right now. We have again a 1,000 gram object or a 1 kilogram object. When I pull this down, I would say that's very close to 2.5 newtons. Okay, 2.5 newtons. Now I would like to show you how these holes work, how the distance works. So first of all, you can see that the first hole is at 5 centimeters, the second hole is at 10, 15, etc. So there's 5 centimeters between each hole. So what I'm going to do is I'm going to move this block, which is right at that hole right there, and I got very lucky that there's a piece of tape there. I'm going to lift it up 1 hole. Okay? Let me see if I can move it just slightly better. You can see the holes there. Okay, so up 1 hole. Okay. Now I'm going to move, how far am I going to move my hand? You can see that one right there. Can't see, my hand's blocking. Okay, so can't see it, can see it right there. So for this to move up 1 hole, my upper hand has to move down 1, 2, 3, 4 holes for this to go up 1 hole. Let me go backwards. 1, 2, 3, 4. 4 down, 1 up. Now now let me show you the logic here. You could have figured that out on your own. There are 4 ropes here. For this to go up 1 hole, or 5 centimeters, each of these ropes has to shorten 5 centimeters, which means I have to pull out 5 centimeters for each support rope, which is a total of 20 centimeters, or 4 holes. Now, by the way, these red ones are just to hold on to it so it doesn't crash. Let's do our analysis now. Let's remember that 1 kilogram equals 1,000 grams. So this is close enough to a 1 kilogram object. I know it was slightly more or less, but there's friction in these pulleys and other things. And we pulled out here 2.5 newtons. Now this, when we lifted it, it went up 1 hole. And we said that 1 hole was 5 centimeters, which is 0.05 meters. Well, here we pulled out 4 holes worth. And if 1 hole is 5 centimeters, then that's 20 centimeters. So that's our distance is 0.2 meters. Well, the potential energy we gained, which is mgh, well, that's going to equal our mass, 1 times the acceleration due to gravity, we'll use 10, and our height, which is 0.05 meters. Well, 10 times 0.05 gives me 0.5 joules change of potential energy. Let's go here and look at the work that was done. Well, work equals force times distance. Our force is 2.5 newtons, and we went a distance of 0.2 meters, which gives us 0.5 joules of work done. Sure looks like the work done equaled our change of potential energy. Let's look at that a different way. I'm going to show you now the relationship between kinetic energy and work. I have a mass here that's going to fall as I let this cart come down this track here. Okay. First thing I need to do though is measure the mass of this object. Let's do that. Here's the mass of our cart. Boy, did I get lucky. Right at 400 grams. I mean, yes, 3.99.8 grams, but come on. 400 grams. It's like the physics gods are smiling at us right now. Obviously, I measured the mass earlier, but I just spliced it in here. Now let's figure out how this photo gate works. For those of you that haven't done this before, let me go ahead and reset it. And watch what happens when I put my finger underneath that photo gate. It's reading time. Oh, it stops. Reading time. Stops. So when there's actually a beam of light in there. When that beam of light is broken, the timer goes. And let's see what's breaking that time. Let's breaking that beam. It's this black wing here on the side. how long is that black wing? Because again, if we're measuring time and we have a distance, we can calculate speed. So let me zoom in on this. So there's from 0, where is it? Sorry, from 0 to a little over 5 maybe? Oh, it looks like 5 centimeters, okay? So the wing is 5 centimeters, so we're going to take 5 centimeters distance divided by the time, and that will give us the speed, okay? So let me go ahead and set this up and we'll run it. Now obviously you can't see this mass fall all the way to the ground from here, but let me go ahead and push this all the way back. So I'll have to stretch over there. Keep this from jangling around. Hit the reset button. Put this up a little bit more. You may or may not be able to see that. We'll get our times here in a bit. Ready? Go. Now let's go ahead and take a look at the times that we just recorded. So the second one, notice the blue one goes into here, the farthest one, reads 0.0326. Can you see that now? There you go. Now, that's the first photo gate. Here's the second photo gate. Notice it's less time because the object was moving, the cart was moving faster. And this one, I have them both set up. That's the time between them. So, first time to go through the first photo gate, time between them, second photo gate. Now, we're also going to need the distance between those two photo gates. Notice this is 980 and 60, so that's at 70. And over here, between the 30 and the 10, that's at 20, or as close as I could get them. So 70 minus 20 obviously is half a meter. So let's calculate our speeds first. Our speed, we actually use V even though we are calculating speed. Through the first photo gate would be our distance, which was the wing, 5 centimeters divided by 100 because there's 100 centimeters in a meter, divided by our time through that photo gate, gives me 0.05 divided by 0.0588, and that gives me, hard to see, 8.85 meters per second. Now what about through the second photo gate? Well, VB will equal same 0.05 meters, but this time divided by that 0.0326 seconds, which gives me 1.53. I believe there was a 0 there. Now notice it did speed up, which should make sense. It was accelerating, and it had a smaller amount of time there. Let's go ahead and let's calculate the kinetic energies here. So our kinetic energy is 1/2 mv squared for each of them, equals 1/2 our mass. Our mass we measured to be 400 grams, which is 0.4 kilograms. Remember, there's 1,000 grams in a kilogram. So I'm just going to put a 0.4 there and 0.85 and make sure to square it. Had a kid once that never squared anything when it came to kinetic energy. I guess let's do it in order here. So we have 0.5 times 0.4 times 0.85 squared, and that gives me 0.1445 joules. And that's our energy beforehand. And our kinetic energy at B afterwards, I guess that's really confusing, I apologize, would be 1/2 0.4 times 1.53 squared, and that gives me 0.5 times 0.4 times 1.53 squared, gives me 0.4682 joules, okay? So our change of kinetic energy, which would be our final minus our initial, gives me, let's go ahead and make sure I have all of the rounding the same. I get 0.3237 joules as my change of kinetic energy, okay? And now we want to calculate work. Well, work equals force times distance, And we should know from Newton's second law that force is mass times acceleration times distance. Well, we have the mass, which is 0.4 kilograms. We have the distance, which is 0.5 meters. But we need to calculate our acceleration. Well, hopefully you remember that acceleration equals change of velocity or change of speed over the time it took. Well, our change of velocity, that would be our final minus our initial divided by our time between the two, the time it took for it to accelerate. And our acceleration in this case gives us, all right, so now let's calculate our acceleration. 3 minus 0.85 gives us the change of velocity divided by our time between them, gives me 1.55 meters per second squared. Well, let's plug all of this into our work. Well, our work, we have our mass, which is 0.4 kilograms, times our acceleration, times the distance, which was 0.5 meters. And that gives us 0.4, 0.55 times 0.5, and that gives us 0.31 joules of work done. Let me write that a little nicer. My 3 was pretty terrible. 0.31 joules. Let's go back and take a look at what we did for our kinetic energy. We got that our change of kinetic energy is 0.32 and our work done 0.31. Now, those numbers are not exact, but they are very, very close. The difference there, roughly, 0.1. Let's go ahead and take 0.3237 minus 0.31 divided by, which one is correct? I don't know. I'm going to use the bigger one. And that's a difference of 4%. And, for all the friction and other things that are in that system, I would say that that's very good. So we have now come up, once again, this is actually what's known as the work kinetic energy theorem. That work done by a force will turn into kinetic energy of an object. In the previous, I guess earlier in this, I guess we'll keep it all in one video, we found out that work equal the change of potential energy, which gives us a theory that you should know. Sorry, this is a law of physics that work equals a change of energy. So whenever there's a change of energy, work must have been done.